Hello everyone, I am Santosh KG, Assistant Professor, Department of Mechanical Engineering, MIT, Mysore. In today's session, I am going to solve some problems on free vibrations which comes under Module 4 of subject Dynamics of Machines having subject code 18ME53. So, the first problem statement is like this: find the natural frequency of a simple pendulum by neglecting the mass of the rod. So, in order to find the natural frequency, as we discussed in earlier classes, we can make use of either the energy method or Newton's second law or Raleigh's method to find the natural frequency. In today's class, I am going to use the Newton's second law in order to find the natural frequency of some of the problems which I am going to solve. So, the problem given is having the following statement, and this is the simple pendulum which is given. So, here we are having a rod of length L. To the end of the rod L, a bob of mass small m is attached, and the other end of the rod it is fixed, it is connected to some fixed point. First, in order to find the natural frequency, what we should do is, first we should give some initial disturbance to the mass. So, this is the initial equilibrium position of the bob. Now, I am going to displace this mass by a small angular displacement, let us say it is theta. So, when I displace the mass m through small angle theta, now let us try to write the free body diagram. So, as we know that on a given system, we are having only one force that will be coming because of this mass which is attached to the end of the rod, and the mass it will be always acting in the downward direction, and the magnitude of the mass is m into g, and this rod is connected to the fixed body at point O. Now, since we have provided the displacement, the angular displacement is provided in this direction. Now, let us try to find what will be the natural frequency of this system. So, in order to find the natural frequency of this system, I will be using the Newton's second law. Mathematically, for the rotary system, the Newton's second law, it can be written as the summation of all the moments at certain point, it should be equals to the mass moment of inertia times the angular acceleration, which we are denoting it by theta double naught. So, in general, we can write the Newton's second law in mathematical form as sigma m equals j naught into theta double dash. Here we are going to take the moment about point O. So, I will write sigma moments, sigma represents the summation of moments about point O, it should be equals to the mass moment of inertia times the acceleration. So, here we can see that on the free body diagram, we are having only one force, that is due to the mass of this bob, and it is m into g, and it will be acting in vertically downward direction. So, in order to find the moment, we should always know the perpendicular distance of the forces from the point where we are going to take the moment. Here we are taking the moment about point O. So, with respect to point O, this mg, let us say it is at a distance of x. So, mg into x, it creates a moment that is going to act in the clockwise direction, but whatever the moment we have applied, in order to displace the bob, it is in counterclockwise direction. So since the moment which is created by the mass of the bob is opposite to that of the displacement of the bob, we can denote it by a negative sign, and the magnitude of the moment will be equals to mg multiplied by the perpendicular distance, which is denoted by x, and this will be equals to j naught, which represents the mass moment of inertia about the point O, and it will be equals to mass of the bob multiplied by the length of the rod, which is given as L. So it is L square into theta double dot, which represents the acceleration. Now we shall try to find what is the value of x. So here if you trace the movement of this bob, it is a circular arc, but the amount of displacement what we have given to the bob, it is very small. So if the value of theta is very small, then the length of this arc will be approximately equals to the length of the straight line that is joining between these 2 points. Now if I draw a straight line here, this straight line with respect to the initial position of the bob, it is making an angle 90 degrees. This length will be equals to x, and then since the amount of displacement is very less, they have given the length of the string. So the length of the rod, it is L. Now in this right angle triangle, we can relate x with L by making use of the sin theta equation. So sin theta, it can be written as a ratio of opposite to the hypotenuse side of the given right angle triangle. So in this triangle, to the theta, the opposite side is x, and the hypotenuse of this triangle is having length L. So whenever the value of theta is very small, then we can write the value of sin theta as approximately equals to theta. So this is because the angle theta is very small. So in place of sin theta, I can write only theta. So this theta will be equals to x divided by L, or x, it can be written as theta times L. So using this equation, I can write it as minus mg. In place of x, I can write theta into L, or L into theta equals mass times L square into theta double dot. Since we are having the one term on either side of the equal sign, what I will do is I am going to send this term which is having negative side towards this side. So when I send this term to the right hand side, then this minus sign will become plus. So on the right hand side, we are having m L square theta double dot. When I send this term to the right hand side, it will become plus m into g into L theta. So on the left hand side, I will be left with no term. So I am going to denote it by 0, or this equation, it can also be written as m L square theta double dot plus m g L into theta, it will be equals to 0. Now what I will do, I am going to divide this equation by this term, that is m into L square. So divide above equation by the coefficient of theta double dot, which is ml square. So when you divide the above equation by ml square, I will be left with theta double dot in the first term plus m into g into l. This is the coefficient of theta. In the second term, I should divide it by m l square into theta equals 0. I am going to call this equation as equation 1, and I will compare this equation with the standard simple harmonic motion equation for the rotational system, which is given by theta double dot plus omega square into theta equal to 0. So when I compare these two equations, we can observe that the value of coefficient of theta in the first and the second term, it is omega square. This is the coefficient of theta in the second equation. This will be equals to the coefficient of theta in the first equation, which is mgl divided by ml square. So L will cancel out, will cancel out, and I will be left with g divided by L, or omega, it can be written as square root of g divided by L. So here omega represents the natural frequency of this pendulum, and it will be equals to square root of g. It represents acceleration due to gravity, and L, it represents the length of the rod, and you will get the natural frequency in terms of radians per second. So this is how we can find the natural frequency of a simple pendulum by making use of Newton's second law. The next problem which we are going to solve now is having the following statement: find the natural frequency of a system shown in figure by neglecting the mass of the rod. Here you can see the system which is given. So the difference between the last problem and this problem is, in the last problem we had only a simple pendulum, that is we are having a rod. To the end of the rod we add one bob which is attached. Here along with the rod and a bob, they have connected one spring having stiffness K to this rod. So it is connected at a distance of A from the point where the rod is fixed, or it is hinged to the fixed support. When the spring is attached to the rod at a distance of A from the fixed support, let us try to see how we can find its natural frequency. So in order to find its natural frequency, again the first step is to write the free body diagram of this given system by displacing the mass through certain angle theta. So first we shall write the initial position, equilibrium position of this given system. Now this is the point to which this rod is hinged to the fixed support. I am going to displace this mass m through a small angle theta. So when I displace the mass through small angle theta, now let us see what are the various forces we are going to get in this system. So which can be represented by means of a free body diagram. So at a distance of A, we are having a spring. So when you are going to pull the mass towards the right side, this spring is going to stretch, and the spring, in order to bring this mass to the equilibrium position, what it will going to do? It is going to apply the force in opposite direction to that of the stretching. So since the stretching is taking towards the right side, the spring, it is going to create a resisting force in the opposite direction, that is towards the left. And what is the amount of spring force that is created by the spring? It can be determined by making use of the spring stiffness formula. So the spring stiffness, it is defined as the force which is required in order to compress the given spring by an amount equal to delta. Or if I want to determine what is the spring force, what I should do? I need to multiply the stiffness of the spring with the amount of deflection. So the deflection, it may be either extension or it may be a compression also. So here initially the spring, it is having this much length. Now it has got stretched through this distance. So since the amount of stretch is this much, I am going to denote this distance by a symbol delta, which represents the displacement of the spring. So if delta represents the displacement of the spring, then the spring force F, it will be equals to K times delta, where K represents the stiffness of the spring. So K delta is the spring force that is developed when we displace the bob through an angle theta. The other force we are going to get is the force M into G, which is acting in vertically downward direction, and from the equilibrium position, let us say it is displaced through an amount which is equals to x. Now before going to the Newton's second law, in order to find the natural frequency, first let us try to find what will be the value of theta and what will be the value of x. So in order to get the value of theta, I will use the triangle, this triangle where the angle between these two sides is given as theta, and the distance between point O to the point where the spring is connected, it is A, and then the distance between these two end points, it is denoted by delta. After writing the triangle, first let us try to name the sides. So the delta, which is opposite to theta, it represents the opposite side, and this line which is opposite to 90 degrees, it represents the hypotenuse, and the side having length A, it is adjacent to theta, so it represents the adjacent side. Now to get the value of delta in this triangle, I can make use of the trigonometric function, which is the ratio of opposite to the adjacent side. So the ratio of opposite to adjacent, it is denoted by tan theta. So tan theta will be equals to the opposite side length is delta and the adjacent side length is A. So whenever the angle are very small, then tan theta, it can be written as theta itself, and it will be equals to delta divided by A, or delta, it can be written as theta times A. So this is the value of delta in terms of A and the amount of displacement theta. Similarly, we can also find what is the value of x. So in order to determine the value of x, I should consider a right angle triangle. Here the length of the rod is given and it is equals to L, and this distance is denoted as x. So in this right angle triangle, the side which is opposite to theta, it is having length x, and the side which is opposite to 90 degrees is L, so it represents hypotenuse, and this side it represents the adjacent side. Now we can relate the opposite to the hypotenuse by using sin theta equation. So sin theta, it will be equals to opposite divided by hypotenuse. So the opposite side is having a magnitude of x, and hypotenuse, it is having a magnitude of L. So whenever the angles are very small, sin theta, it can be written as theta, and it will be equals to x divided by L, and to get the value of x, I should send L to the left hand side, thereby we will get the value of x as theta into L. So here the value of delta, it is a times theta, and the value of x, it is L times theta. Now in order to calculate the natural frequency of this system, we will be using the Newton's second law. So the Newton's second law, it states that the summation of moments, it should be equals to the mass moment of inertia times the acceleration, which is theta double dot. So here we are going to take the moment about point O, therefore the moment about point O equals J naught times theta double dot. So since we are having two forces, we will get two moments. One moment due to the mass of the ball, and second moment is due to the spring mass. So the moment due to these forces will be taken as positive if the moments, they are acting in the direction of the displacement. So here the angular displacement, it is given in counterclockwise direction. So if the moments due to this mg and k delta, if they are creating the counterclockwise moments, then they should be considered as a positive moments. If the moments due to these forces, they are creating a clockwise couple, then it should be taken with a negative sign. So first I will consider the moment due to the force mg. So the force mg multiplied by the perpendicular distance of this force from the point O. So the perpendicular distance of this force mg from point O is x, and this force is going to rotate the bob in clockwise direction. So if the moment is clockwise, then for the given configuration, it should be written with a negative sign. Similarly, now let us try to find what will be the moment due to the spring force K delta. So the moment due to the spring force, it can be calculated by multiplying the spring force K delta with the perpendicular distance of this force from point O. Here the spring force, it is acting in horizontal direction. So since it is acting in the horizontal direction, the perpendicular distance of this force from point O, it will be a vertical length, and this length in the problem, it is stated as A. So for K delta, if I multiply A, then I will get the moment due to the spring force K into delta. Now in order to decide whether I should write a positive sign or negative sign in front of this spring force, I should see whether the moment it is acting in clockwise direction or the moment is in counterclockwise direction. Here this K into delta force is trying to rotate this rod or the bob in clockwise direction. So since the moment due to the spring force, it is clockwise for this configuration, then it should be written with a negative sign. So this it should be equals to J naught. So J naught represents the mass moment of inertia about point O. It will be m times L square into theta double dot. Now let us substitute the values of x and delta in the above equation. So x, it can be written as L into theta minus k into the distance delta. It can be substituted by a into theta into a. This will be equals to m L square into theta double dot. Again mg L into theta minus k into a, it is a square theta. This will be equals to m into L square theta double dot. So I will send these two terms towards the right side. So when I send these two terms towards right side, I will get the equation m L square theta double dot. This term, when it goes to the right side, it becomes plus mgl into theta. So when this term it comes to the right side, it becomes plus k into a square theta, and on the left side I will be left with O, that is 0. I will rearrange the terms. So m L square into theta double dot plus, if you consider these two terms, they are having theta in common. So if I take theta as a common in these two terms, I will be left with mgl plus k into a square into theta. So this will be equals to 0. Now in order to compare this equation with a standard SHM equation for the rotary system, that is theta double dot plus omega square into theta equals to 0. What I should do? I should make the coefficient of theta double dot as 1. So if I want to make the coefficient of theta double dot as 1, I need to divide this equation by the coefficient of theta double dot, which is m into L square. So next step is divide the entire equation by m into L square. So when I divide the entire equation by m into L square, in the first term I will be left with theta double dot, and in the second term, in the numerator I am having m into g into L plus k into a square divided by, in the denominator I am having m into L square equals 0 divided by anything will be 0. Now if I compare this equation with the standard equation of simple harmonic motion for rotary system, that is theta double dot plus omega square into theta equals to 0. So I will consider this as equation 1 and I will consider this as equation 2. So when you compare these two equations, we can see that the coefficient of theta double dot on both the equation, it is 1 itself, and on the right hand side we are having 0. Thereby we can equate the coefficient of theta on the first and second equation. So when I equate the coefficient of theta in first and second equation, I will get omega square equals mgl into L plus k a square divided by m L square. So here omega represents the natural frequency, therefore omega equals, if I send this square on the right hand side it will become square root. So, omega will be equal to square root of mg into L plus k into a square divided by ml square. So, this represents the natural frequency of the given system in terms of radians per second.